For more than 100 years, the world of paleontology was shaped by a simple, elegant idea that all dinosaurs could be neatly divided into two great branches, Saurischia and Ornithischia. This division, first proposed in the late 19th century, became the backbone of how scientists understood the incredible diversity of these ancient reptiles. The key to this classification lay in the structure of the dinosaur pelvis. By examining fossilized hip bones, researchers believed they could unlock the secrets of dinosaur evolution and relationships. It seemed like a rock-solid foundation for organizing the vast and varied dinosaur family tree. Saurischians, whose name means lizard-hipped, were defined by a pelvis in which the pubis bone pointed forward, much like the hips of modern lizards. This group was incredibly diverse, ranging from small, agile predators to the largest land animals to ever walk the earth. Among the Saurischians were some of the most famous dinosaurs of all time. The terrifying Tyrannosaurus rex, with its massive jaws and tiny arms, and the gentle, long-necked Brachiosaurus, towering above the treetops, both belong to this branch. Their fossils have captured the imagination of scientists and the public alike for generations. On the other side of the dinosaur family tree stood the Ornithischia, or bird-hipped dinosaurs. This group was just as remarkable, filled with a dazzling array of plant-eating species that developed unique adaptations for survival. The defining feature of Ornithischians was their backward-pointing pubis bone, a trait that, at first glance, seemed to link them to modern birds. This similarity in hip structure led to their name, but as we'll see, appearances can be deceiving. Ornithischians included some of the most iconic herbivores in history: the stegosaurus, with its double row of bony plates and spiked tail, and the mighty triceratops, armed with 3 formidable horns and a massive frill, are just 2 examples of the group's incredible diversity. For decades, this straightforward classification, based on the elegant simplicity of hip structure, was accepted as scientific fact. Textbooks, museum displays, and generations of paleontologists relied on this system to make sense of the dinosaur world. But as is often the case in science, new discoveries began to challenge the old ideas. Nature, it turns out, rarely fits into the tidy boxes we create. Despite their name, the bird-hipped dinosaurs were not the ancestors of modern birds. This surprising fact puzzled scientists and hinted that the story of dinosaur evolution was far more complex than anyone had imagined. The real ancestors of birds were hiding in plain sight among the lizard-hipped theropods. Fossil discoveries of feathered dinosaurs and ancient bird-like creatures began to blur the lines between these groups, deepening the mystery of avian origins and forcing scientists to rethink everything they thought they knew. This unexpected twist set the stage for a scientific revolution. The dinosaur family tree, once thought to be settled, was shaken to its very roots as paleontologists raced to piece together the true story of dinosaur evolution. The discovery that birds descended not from the bird-hipped dinosaurs, but from the lizard-hipped theropods like Velociraptor, added a fascinating new chapter to the tale. It revealed that the path from dinosaur to bird was full of unexpected turns, and that the story of these ancient creatures is still being written today. The idea that birds are actually the descendants of dinosaurs was once dismissed as a wild theory, even among scientists. For decades, the prevailing view was that birds and dinosaurs were 2 entirely separate branches on the tree of life, with little in common beyond a distant reptilian ancestor. The thought that the sparrows and pigeons we see today might be living dinosaurs seemed almost impossible to believe. However, everything began to change in the late 20th century, thanks to a remarkable series of fossil discoveries. In particular, the unearthing of exquisitely preserved feathered dinosaurs in the Liaoning province of China provided the missing pieces of the evolutionary puzzle. These fossils, some with feathers so well preserved that individual barbs and filaments could be seen, offered undeniable evidence that feathers were not unique to birds. Dinosaurs like Microraptor, with its 4 wings, and Sinosauropteryx, sporting a fuzzy coat of primitive feathers, revealed a stunning diversity of plumage. Some had simple hair-like filaments, while others boasted complex veined feathers similar to those of modern birds. These adaptations may have served a variety of functions, from insulation and display to, eventually, the mechanics of flight. The most astonishing revelation was that these feathered dinosaurs were members of the theropod group, a branch of the Saurischia, or lizard-hipped dinosaurs. This group also includes the mighty Tyrannosaurus rex and Velociraptor, making it clear that the line between bird and dinosaur was far blurrier than once thought. what's truly fascinating is that birds, with their so-called bird-hipped pelvis, actually evolved from ancestors with a lizard-hipped configuration. This means that the classic distinction between lizard-hipped and bird-hipped dinosaurs doesn't reflect the true evolutionary relationships. Over millions of years, evolutionary pressures led to dramatic changes in hip structure, allowing for the development of new ways of moving, nesting, and eventually flying. This transformation is a powerful example of how adaptable and innovative life can be, constantly reshaping itself in response to new challenges and opportunities. The discovery of feathered theropods not only cemented the evolutionary link between dinosaurs and birds, but also revealed that the story of dinosaur evolution is far more intricate than the simple Saurischian-Ornithischian divide. It suggested that features like feathers and warm-bloodedness may have been more widespread among dinosaurs than previously imagined. As a result, scientists were compelled to redraw the dinosaur family tree, rethinking long-held assumptions about how these ancient creatures were related. The boundaries between groups blurred, and new questions emerged about the origins of flight, feathers, and even the behaviors of these fascinating animals. The world of paleontology found itself on the brink of a paradigm shift, as each new discovery promised to rewrite the story of how birds, the only living dinosaurs, came to rule the skies. In 2017, a groundbreaking study led by Matthew Barrett and colleagues shook the foundations of dinosaur classification. They proposed a radical reorganization of the dinosaur family tree, suggesting a new group called Ornithocelida. This new grouping challenged the long-held Saurischian-Ornithischian dichotomy. Instead of two distinct lineages, their analysis of numerous anatomical features, including those of early dinosaurs, suggested that theropod dinosaurs like Tyrannosaurus rex were more closely related to ornithischian dinosaurs like Triceratops than to sauropod dinosaurs like Brachiosaurus. This proposed a fundamental realignment of the dinosaur family tree. The Ornithocelida hypothesis sent shockwaves through the world of paleontology. It challenged over a century of established knowledge and forced scientists to reevaluate their understanding of dinosaur evolution. This new family tree suggested that many traits once considered defining characteristics of certain groups might have evolved independently or been lost and regained over time. The implications of this new arrangement were far-reaching. It meant that features shared by theropods and ornithischians, such as feathers, a herbivorous diet, and even certain skeletal structures, might be ancestral to both groups rather than independently evolved. This new perspective had the potential to rewrite our understanding of dinosaur evolution. The Ornithocelida proposal ignited a fiery debate within the paleontological community. Some scientists embraced this new paradigm, excited by the prospect of rewriting dinosaur history. They pointed to the compelling anatomical evidence and the potential to explain previously puzzling evolutionary patterns. However, other researchers remained skeptical, defending the traditional Saurischian-Ornithischian classification. They argued that the new study might have misinterpreted certain anatomical features or that the data set was not robust enough to support such a radical change. This debate highlighted the dynamic nature of scientific discovery, where new ideas are rigorously tested and debated before gaining wider acceptance. The debate surrounding Ornithocelida has fueled a surge in research as paleontologists seek more evidence to support or refute this new family tree. Every new fossil discovered, every new anatomical study conducted, has the potential to tip the scales in favor of one hypothesis over the other. New technologies like CT scanning and 3D modeling are allowing scientists to study fossils in unprecedented detail. By creating virtual models of dinosaur skeletons, they can analyze anatomical features with greater precision and compare them across different species. This surge in data and the application of cutting-edge technologies promise to provide a clearer picture of dinosaur relationships in the years to come. The Ornithocelida hypothesis has prompted a reevaluation of how we interpret certain dinosaur traits. If theropods and ornithischians are indeed more closely related than previously thought, it suggests that features once thought to be unique to one group might have a deeper evolutionary history. For instance, the presence of feathers, once considered a hallmark of theropods, might have been present in the common ancestor of both theropods and ornithischians. This means that early ornithischians, even those that evolved into massive herbivores, might have possessed some form of feathering. This challenges our traditional image of these dinosaurs and opens up exciting possibilities for understanding the evolution of feathers and their functions beyond insulation and flight. The debate over the dinosaur family tree, particularly the placement of theropods, has fascinated paleontologists for decades. As new discoveries are made and old fossils are re-examined with advanced technology, our understanding of dinosaur relationships continues to evolve. The question of how theropods and ornithischians are related is more than just a matter of classification. It has significant implications for understanding the origin of birds and the evolutionary pathways that shaped their development. If the Ornithocellular hypothesis proves correct, it suggests that the bird lineage inherited a unique set of characteristics from its dinosaurian ancestors, traits that may have set the stage for the emergence of entirely new forms of life. This inheritance could include features like feathers, a bipedal stance, and specialized skeletal structures that provided the foundation for later evolutionary innovations. These adaptations, such as lightweight bones and advanced respiratory systems, may have enabled the evolution of flight and allowed some dinosaurs to thrive in new ecological niches. By unraveling the intricate relationships between different dinosaur groups, scientists can trace the origins of key evolutionary traits and better understand how these ancient creatures adapted to their environments over millions of years. Each fossil discovery adds a new piece to the puzzle, helping us gain a clearer understanding of the evolutionary processes that led to the incredible diversity of these Mesozoic giants, from towering sauropods to agile predators. These evolutionary transitions ultimately gave rise to the birds we see today, connecting the distant past to the present in a remarkable story of survival and transformation. The dinosaur family tree is not merely a static chart, but a dynamic representation of life's grand evolutionary journey, constantly updated as new evidence comes to light and our scientific understanding deepens.